Hello future engineers, subscribers, viewers, and students. Here is another video in plane and solid geometry. This is the last part, part 4. And in this part, I'm going to discuss the principles and formulas for spheres and its families. Then let's have the common solids of revolution, Pappus propositions, ellipsoid, and problems to be discussed. So as for sphere and its families, the volume of sphere, of course, the formula can be derived using integral calculus. So we define a sphere as a solid. All points on its surface are equidistant from its center point. So the volume is equal to 4/3 pi r cubed, and the total surface area is 4 pi r square, and the volume is also pi over 6 diameter cube. It's simpler to look at, but it's up to you which formula you use in times when the volume is needed. Of course, you should use the one that is convenient to you to use. So the total surface area is 4 pi r square, and in terms of the diameter, it is pi diameter square. So it appears that in terms of the diameter, the formulas would be more compact and simpler. Also note that the ratio of the volume to surface area is 1/3 of the radius. Again, volume of sphere to the total surface area is 1/3 of the radius. Next, we define portion of sphere, which is the skin area. We define it as the portion of the spherical surface bounded by halves of two planes of great circles, and it is a skin area of watermelon slice. When you slice a watermelon perfectly, the skin area, the green one, is the spherical lune, and the resulting solid is called spherical wedge. So this is the angle between the dihedral planes, theta, and that's the spherical lune, the area, skin area, and this is the spherical wedge, the solid as a whole. So for the area of the lune as to theta, you don't need to memorize. You just proportion the area of the lune as to the angle between the dihedral planes theta equals area of the sphere 4 pi r square as to 2 pi if theta is in radians, and it is equal to 4 pi r square over 360 degrees if theta is in degrees. So the resulting formulas for area of the lune would be as follows. But as I said, you don't need to memorize these formulas. Just remember how these formulas are arrived at. Then for the volume of the wedge, volume of wedge as to theta equals volume of sphere 4/3 pi r cube as to 2 pi if theta is in radians, then 4/3 pi r cube as to 360 degrees if theta is in degrees. And the formulas would be as follows. But I don't also want to memorize these formulas. I'll just apply this proportioning of the angle so that I can conveniently apply the formula or derive the formula. So we define a spherical wedge as that portion of a sphere bounded by a lune and the planes of half circles of the lune called dihedral planes. Then we define next a spherical zone, which is that portion of a spherical surface between two parallel planes. And a spherical zone of one base has one bounding plane, which is a small circle. So this is the sphere, and we have a bounding plane here and the surface of the sphere. This is a spherical, the area is spherical zone, but the solid as a whole is called spherical segment with one base. So that's the zone. The radius of the sphere is noted by capital R. The radius of the small circle is small a. The height is h. And that's the zone. Then this is the solid is spherical segment. Then for the lower part, it is also a spherical segment, the solid, and the surface area, excluding the area of the small circle, is called the zone. So zone is 2 pi rh. You can derive this by integration rather. Then volume of spherical segment of one base is pi h squared over 3 times quantity 3r minus h, also derived by integration. Then for zone 1, which is the lower part here, with height h1, so z sub 1 is 2 pi r h1, or it is equal to the surface area of sphere minus the zone area 2 pi rh. And the volume is pi h1 square over 3 quantity 3r minus h1, or it is volume of sphere minus volume of spherical segment, this spherical segment volume there. Then if we have a spherical zone with two bases, the zone area is still 2 pi rh. H this time is the distance between parallel bases, which are small circles. So here it is. So that's a spherical zone with two bases. The radius is still r. The distance between parallel bases is small h. Then the radii upper radius is b. The lower radius is a. And the zone is still 2 pi rh. And the volume is pi h over 6, quantity 3a square plus 3b square plus h square. So that's the zone area, so 2 pi rh. The volume of the solid with two bases, spherical segment with two bases, is pi h over 6, quantity 3a square plus 3b square plus h square. We can still apply this formula for a spherical segment of one base. We just set b 0. So it is pi h over 6 quantity 3a squared plus h squared. So that's the volume and zone area. For spherical segment with one base, this formula here can be reduced to pi h over 6 quantity 3a squared plus h squared, which is the same as this supposedly. Next family of a sphere is called spherical sector or spherical cone. So for it to qualify as spherical sector or cone, the vertex of the conical part should be the center of the sphere, or else it's not a spherical sector or cone, and the formulas here won't be applicable for that case. So for instance, the vertex is somewhere here. So it appears to be a spherical sector, but it's not. So the formula is not applicable. But it consists of a cone and a spherical segment. So the spherical segment need not lie on the sphere. So that's it. So the volume is 2/3 pi r square h, and we're going to derive that also. So we have here the height of the spherical segment part, and the radius of the sphere is r. So if this angle is theta over 2, then supposedly this is r minus radius of the sphere minus h. Since h is r, uh, radius, this is supposedly radius minus h, and h is radius of the sphere minus this part, which is r cosine theta over 2. So h therefore is quantity r, so it is equal to r, radius of sphere, quantity 1 minus cosine theta over 2. So though the volume is 2/3 pi r square h, which I'm going to derive also. A is the radius of the small circle, by the way. So replacing h by r times quantity 1 minus cosine theta over 2, then the volume becomes 2/3 pi r cubed times quantity 1 minus cosine theta over 2. Then the total surface area consists of area of the lateral area of the cone plus zone area. So the lateral area of the cone, if you can recall, is pi times radius of the base of the cone, which is a here. Slant height would be the radius of the sphere, so pi ar plus zone area 2 pi rh. So volume is also 2/3 pi r cubed, quantity 1 minus cosine theta over 2. After we replace h by r, quantity 1 minus cosine theta over 2 from the figure, then total surface area is pi ar plus 2 pi rh. So those are the volumes and formulas for that spherical sector or spherical cone. So in general, the volume is also 1/3 as long as it is from sphere, 1/3 of z sub s times radius of the sphere. So it's like volume of pyramid where the area is replaced by z sub s. This z sub s is the area on the portion of the sphere. It may be a spherical segment, a spherical zone rather, or spherical triangle whatsoever. So z sub s is a surface area in the portion of the sphere. So if it is zone area, then 2 pi rh, then it will go back to this formula for the volume. If it is a spherical triangle, so you just replace this by area of spherical triangle, which is pi r square spherical axis divided by 180 degrees. So recall from plane geometry. So again, the volume is volume of spherical sector or cone is equal to volume of cone plus volume of spherical segment of one base. The volume of the cone is 1/3 pi a square times the height, and the height is big radius minus h, then plus the volume of spherical segment pi h square over 3 quantity 3r minus h. So volume of spherical cone is pi a square times quantity r minus small h over 3 plus that's volume of the cone, conical part, plus volume of spherical segment pi h square over 3 quantity 3r minus h. Then by Pythagoras theorem, this a square here is equal to big R square minus this height quantity square. This height is big R minus small h. So A square is big R square minus quantity big R minus small h quantity square. Simplifying, this is equal to 2RH minus h square after canceling out big R square. Substitute into this equation, and before we substitute, we factor out pi over 3, and in this part we expand this part, h squared times quantity 3r minus h. So volume is equal to pi over 3 times quantity 2rh minus h squared times quantity r minus h plus 3r h squared minus h cubed. So if we expand this inner terms in the brackets, so we have 2r squared h, then minus 2rh squared minus rh squared plus h cubed. Then we just copy these last two terms. So volume of spherical segment is pi over 3 quantity 2r squared h minus 2rh squared minus rh squared plus h cubed, then plus 3rh squared minus h cubed. So cancel out h cubed. This 3rh squared and negative 2rh squared, negative rh squared is negative 3rh squared, so we'll cancel. So the remaining term is just this one. And 2r squared h times pi over 3 is 2/3 pi r squared h. So that's why the volume of spherical sector or spherical cone is 2/3 pi r squared h. Then we have common solids of revolution. So the first solid of revolution that we shall consider is the torus or the donut, which is a solid formed when a circle is revolved about an axis away from the circle. So that's the cross section of the torus or donut. Then revolve it about a vertical axis away from it. This axis should not cross the circle, so that the second theorem of Pappus-Olgini can be applied, and the distance is big R. The radius of the circle is small r. Then volume equals pi small r square times distance traveled by the centroid is 2 pi big R. So volume pi small r square times 2 pi big R. So the volume, you don't need to memorize, just concentrate on the second proposition of Pappus, that volume is equal to area of the region times distance traveled by the centroid of that region. Then you will have 2 pi small r times 2 pi big R for the total surface area. Rather, this is the circumference, 2 pi small r. Then distance traveled by centroid is the same, because the centroid of the circle as area and the centroid of the arc of the circle is the same. They are coincident. So these are the resulting formulas, but as I said, you don't need to memorize. Just apply the propositions by Pappus. Then we'll have the paraboloid of revolution, which is a solid formed by rotating a parabolic segment or parabola about its axis of symmetry. We can apply these Pappus propositions to derive the volume of paraboloid of revolution if it is a parabola. If you can locate the location of the centroid from the axis, which is 3/8 of the radius, and that is if there is only one base. But if there are two bases, you have to apply integral calculus to derive the formula for the volume, which is pi over 2 quantity big radius square plus small radius square times the distance between the bases with the radii is big R and small r. So this is the paraboloid of revolution with two bases. One base has radius big R and the other one has radius small r, and the distance between these bases is small h. Then volume is pi over 2 quantity big R square plus small r square times h over 2. If there is only one base, so you just set small r equals 0, then the formula is pi over 2 big R square times h. If you're going to interpret that result, that volume of paraboloid of revolution with one base is equal to half the volume of the right circular cylinder that circumscribes about that paraboloid of revolution. So if this is y, from the vertex to that lower base small r of radius small r, then you remember squared property of parabola, which is y as to r small r square equals y plus small h as to big R square. That's squared property of parabola. And this is what I mentioned earlier, that the volume of paraboloid of revolution with the single base, you just set small r to 0, is equal to half the volume of the circumscribing cylinder. So that's it. So since the volume of this paraboloid of revolution is 1/2 the volume of the circumscribing cylinder, it follows that this volume here, that is outside the paraboloid but inside the right circular cylinder, has the same volume as the volume of the paraboloid of revolution. So take note of that property or fact. So pi r square h over 2, if you're going to interpret this, this is half the volume of the circumscribing cylinder. And also take note that the volume, which is this, outside the paraboloid of revolution but inside the right circular cylinder, is also the same as that. So that volume plus volume of paraboloid is volume of the right circular cylinder. So we have here the Pappus propositions. The first one states that the surface area generated by a curve is equal to the product of the length of the curve and the distance traveled by the centroid of the curve. So it doesn't mean that the surface area or the rotation or the movement of the centroid of this curve here is one complete revolution. It may be partial of a revolution. And for the length of the path traveled by the centroid, it is equal to the radius of the path times the central angle or the angle swept by that centroid, and it should be expressed in radians. The second proposition states that the volume generated by a region is equal to the product of the area of the region and the distance traveled by its centroid. So it is the same as this. It just replace arc or length of curve by area of the region. So for ellipsoid, the volume is 4/3 pi ABC in general. So we have three different radii in different directions, perpendicular directions, A, B, and C. So if A is the major axis, then if we have a semi-ellipse which includes the semi-major axis and the minor axis B, it is revolved about the major axis, then we say that B is equal to C, C is equal to B. Therefore, it looks like an egg shape. So the solid generated would be like an egg. So the volume, we call that, by the way, prolate spheroid when the semi-ellipse, including the major axis, is revolved about the major axis. Then the resulting solid is called prolate spheroid. And the volume is 4/3 pi AB square, because we simply replace C by B. B is equal to C in that case. Because remember, the semi-ellipse, the upper semi-ellipse or the lower semi-ellipse, is revolved about the major axis. So that's why B equals C. So the shape is like an egg. Then for when the semi-ellipse, including the major axis, is revolved about the minor axis, it is called an oblate spheroid. In that case, A is equal to C or C is equal to A. So the volume becomes 4/3 pi A square B or B A square. So it is A that is squared because A equals C. And remember, the semi-ellipse is revolved about the minor axis. So we call that oblate spheroid, like the spaceship of Aliens, Skylab. Or like it's an perfect hamburger like shape. Or for there are shapes of the same as this, like Nips chocolate. Or in short, this is the shape that that is almost the same shape as that of the Earth, oblate spheroid. So therefore, because A is the longest, this is the semi-major axis, and it is squared here, the oblate spheroid has greater volume than the prolate spheroid. So as an demonstration of these two propositions by Pappus, let's derive the volume of sphere, which is 4/3 pi r cubed. And you can only derive this by this approach, not by integration, if you know the location of the centroid of a semicircle from the diameter, which is 4r over 3 pi. And I hope you remember that. So if this centroid is revolved about the diameter, it will generate a circle, and the perimeter or circumference of that circle is 2 pi times this radius of revolution. So volume therefore is area of semicircle pi r square over 2 times 2 pi times quantity 4r over 3 pi. So cancel pi, cancel 4, cancel 2. So the result is 4/3 pi r cubed. That's the volume of sphere. You can also use these Pappus propositions if you know the volumes and areas, but you forget the location of the centroid. So for instance, you do not know the location of the centroid of the semicircular arc. In this case, I'll call it y, so that the distance traveled by the centroid would be 2 pi y, but the length of the arc is half the circumference of the circle, which is pi r, and the surface area generated would be 4 pi r squared. So area S is 4 pi r squared, and it is equal to the length of this curve, which is pi r, times distance traveled by the centroid, 2 pi y. So solving for y is equal to 2r over pi. So that's the location of the centroid of a semicircular wire from the diameter. Homogeneous semicircular wire from the diameter. So that's the end, and I'll consider two problems in this video. So the first one is we have this problem: 3 spheres of radii 10, 20, and 30 centimeters respectively are melted and formed into a single sphere. Find the surface area of the single sphere. So we first determine the radius of the single sphere. Because the spheres are melted, so it will form a single sphere, and the radius is denoted by big R. So we equate the total volume of the 3 spheres to the volume of a single sphere. The surface area is 4 pi r square of a sphere. So 4/3 pi, so the combined volume 4/3 pi times quantity 10 cube plus 20 cube plus 30 cube equals 4/3 pi times r cube. So cancel out 4/3 pi and solve for r. Big R is equal to 33.02 centimeters. So the surface area is 4 pi times 33.02 square. So surface area is equal to 13,701 square centimeters. Then for the second problem, a spherical wooden ball 15 centimeters in diameter sinks to a depth of 12 cm in a certain liquid. So determine the exposed area. So if you're going to imagine that exposed area is zone of sphere, then the exposed height would be equal to 15, the diameter, minus the submerged depth, which is 12, so 3. Then zone area or zone is 2 pi RH, where R is equal to the radius of the spherical wooden ball, which is 7.5 cm, and H is 3, 15 minus 12, 3. So zone area is 2 pi times 7.5 times 3. So the exposed area or the zone is 141.4 square centimeters. So that's it for this video.